Hello dear students, welcome back to physics online session. So today we will be discussing on one of the major chapter in electromagnetic theory, so that is electromagnetic induction. So from that electromagnetic induction only, so we can able to produce that current in a bulk aspect. So before going to understand that electromagnetic induction, so basic things I need to understand first. So those are magnetic flux and changing magnetic flux concept. So let me begins with the chapter electromagnetic induction. Electromagnetic induction. So in case of that electromagnetic induction, so I need to start with the basic aspect, so that is magnetic flux here. Magnetic flux. So it is represented by the symbol phi of B. What's that magnetic flux? So similar to that of electric flux, the total number of magnetic field lines are crossing the surface. Normally we can call it as a magnetic flux here. So look at here. For example, this is one surface area I will consider. So the number of magnetic field lines are crossing this surface here. So these are all represents that magnetic field line here. So it represents that magnetic field lines. So mathematical approach for that magnetic flux. So phi of B is equivalent to a B into A into cos theta. What is the mathematical expression here? Phi of B is equal to B into A into cos theta, where B represents that magnetic field or magnetic induction. So B represents that magnetic field, or we can call it as a magnetic induction. Magnetic induction, magnetic field or magnetic induction here, where A is nothing but a area of cross section of the coil or area of the coil. So now let me consider theta represents what? So theta represents that angle between magnetic field line and normal line. What's the mean of normal line here? So normal line is nothing but, so I have to draw a perpendicular line for this surface here. So for example, treat this is one surface here. So for this surface I want to draw one normal line. So nothing but perpendicular line. So this perpendicular line is nothing but a normal line here. What's that theta represents here? Theta represents that angle between magnetic field line and normal line. Theta represents that angle between magnetic field line and normal line here. So for example, let me consider here. So this is magnetic field line direction. So this is one surface. What is the angle between magnetic field line and surface here? Magnetic field line and surface are perpendicular here. Is it right? So what is the angle between magnetic field line and the surface here? So magnetic field and surface is perpendicular. Then what is the value or what is the angle between magnetic field line and that normal line here? So in order to understand that, for example, this is one surface. For this surface I need to draw one normal line here. So this is act as a normal line. Is it right? So theta represents that angle between magnetic field line and normal line. So this one is magnetic field line. So this is surface here. For this surface I drawn one normal line here. Now tell me that what is the angle between magnetic field line and normal line? Which is normal line? This is normal line. What is this? So this is magnetic field. What is the angle between magnetic field line and normal line? So that is theta is equal to 0 degree here. So hope you are understanding here. So now let me consider that changing magnetic flux. Changing magnetic flux. So changing magnetic flux means delta of phi I will consider. So changing magnetic flux means final magnetic flux minus of initial magnetic flux. For example, initial magnetic flux I will consider if number of turns are there, NBA cos of theta 1 phi of 2, it is equal to NBA cos of theta 2. So let me find out that changing magnetic flux value. So delta of phi is equal to what? phi of 2 minus of phi of 1, final magnetic flux minus of initial magnetic flux. So NBA cos of theta 2 minus of NBA cos of theta of 1 here. So let me consider that delta of phi is equal to what? NBA cos of theta 2 minus of cos of theta 1. So this is the required formula for changing magnetic flux here. So what's that changing magnetic flux formula here? Phi of B is equal to N into B into A cos of theta 2 minus of cos of theta 1. So I said that theta represents that angle between magnetic field line and normal line here. So now let me consider that if theta 1 is equal to 0 degree and theta 2 is equal to 90 degree, what is the change in magnetic flux value? So delta of phi is equal to what? N into B into A. So theta 2 is nothing but what? How much? So that is 90 degree. Cos 90 is what? 0 here. So minus of cos of theta 1. So theta 1 value is 0 here. Cos 0 means 1 here. So that is phi of B is equal to minus of N into B into A here. So if theta 1 is equal to 0. So what's the mean here? So theta 1 is equal to 0 means angle between magnetic field line and normal line. So angle between magnetic field line. So for example, this is magnetic field line. So this is the surface, means for this surface this is the normal line. So theta 1 is equal to 0 degree here. Okay, next one, theta 2 is equal to 90 degrees. So for example, if this is the surface, means so I will tilt by certain angle here. Now look at here, what is the angle between magnetic field line and the surface here? Both are parallel here. So this is perpendicular and this is the parallel here. So magnetic field line and that surface is parallel. Then what is the angle between magnetic field line and normal line? So this is 90 degree here. So this is 90 degree. Next one, if theta 2 is equal to 90 degree and theta 1 is equal to 180 degree. Okay, in this way, so delta of phi is equal to what? So delta of phi is equal to what here? So NBA as it is, shall I write it here? N into B into A cos of theta 2. So theta 2 is value how much? So that is 90 degree. Sorry, theta 2 is, sorry, theta 1 is, theta 1 is equal to 90 degree and theta 2 is equal to 180 degree. Here cos of 180 is nothing but what? Minus of 1 minus of cos of theta 1. Theta 1 is how much? So that is 90 degree. Cos 90 means what? 0. So what's that answer here? So delta of phi is equal to, again delta of phi is equal to minus of 1 minus of N into B into A. So in this case also minus N into B into A. In this case also minus of N into B into A. Next one, if theta of 1 is equal to 0 degree, theta of 2 is equal to 180 degree, then what about the change in magnetic flux? Let me look at here. N into B into A cos of theta 2. So theta 2 is how much? Minus of 1 minus of cos of theta 1. So theta 1 is nothing but what? 0 degree. Cos 0 means what? 1 here. So look at here, delta of phi is equal to N into B into A minus 1 minus 1. So that is minus 2. So delta of phi is equal to minus of 2 times of N into B into A. So this is all about a changing magnetic flux here. So in case of that moving charges and magnetism, we learnt about a Oersted experiment. So from that Oersted experiment, we got one conclusion. So whenever current is flowing in that any conducting wire, around that current carrying conductor, magnetic field will get produced here. So look at here. So from that Oersted experiment, so for example, so this is one wire I will take. So whenever that current is flowing in this wire, so around that current carrying conductor, magnetic field will get produced here. So around that current carrying conductor, magnetic field will get produced. So from that Oersted experiment, what is the generalized meaning I need to understand here? Current can produce the magnetic field. current can produce magnetic field here. Current can produce magnetic field. Then, so after that Oersted experiment, so one more scientist, so that is Michael Faraday. So he gave that maximum contribution in case of a electromagnetic theory. So nowadays, whatever that electricity you are producing in a bulk aspect, so that is all about a contribution of Faraday experiment. So then what was the Faraday experiment I need to understand here. So Oersted, he said that current can produce the magnetic field. So Faraday, he thought that reverse manner of Oersted experiment. So reverse manner means, so current can produce the magnetic field means, so Michael Faraday, he thought that whether magnet can produce the current or not. So what was that Michael Faraday experiment here? So Faraday experiment. So in case of that Faraday experiment, he thought that whether a magnet can produce the current or not, or whether a moving magnet can produce the current or not. He thought that whether I can able to get the current by the magnet or not. So for that purpose, so he made one small experiment. He took that one copper wire, so he wounded that copper wire in a spiral manner here. So all of you know about that experiment, so just within a 2 minutes I can recall it. So this is one galvanometer. So this is a copper coil. So nearby this coil, so I will consider that magnet here. So magnetic field lines are north to south direction here. So whenever that magnet is moving towards the coil, or when the magnet is taking away from the coil, then galvanometer will start showing the deflection here. So galvanometer showing the deflection means there exists a current in the circuit. It means that whether that magnet is moving towards the coil or away from the coil, so then there exists a EMF or current is produced in the circuit. So that is Faraday first law. What is that Faraday first law here? Whenever magnetic flux linked with the circuit changes, then EMF is induced. That induced EMF is lost as long as magnetic flux changes continuously. So remember one point here. In order to get that EMF here, so in this experiment I am getting EMF only when magnet is moving towards the coil or away from the coil. It means that only a moving magnet can induce the EMF. It means that magnet is moving means magnetic flux value is getting changes here. So changing magnetic flux can induce the EMF. So the simpler meaning I need to understand here. So changing magnetic flux can induce the EMF. So changing magnetic flux can induce the EMF here. So I know the formula for flux value. So phi is equal to what? B into A into cos theta. So look at here. So magnetic flux, so changing magnetic flux can induce the EMF, I said. So in order to get the EMF, I need to change the flux value. How to change the flux value? It means that flux value depends on what are the factors here. So flux value depends upon the magnetic induction, it depends upon the area of the coil, and it depends upon the theta, so rotation here. So in order to get that EMF, I need to change the flux value here. How to change the flux value here? By changing magnetic field value, so flux will get changes. By changing the area, flux will get changes. By changing the angle, flux will get changes. So in order to change the flux value, I need to change that field value, I need to change that A value, and I need to change that theta value. If I vary these quantity, then flux will get changes here. So when the flux will get changes means, so I said that changing flux can induce the EMF. So when flux changes means EMF will get produced here. So this is about a Faraday first law here. What that Faraday first law here? Whenever magnetic field linked with the circuit changes. So when magnet is moving towards the coil or away from the coil, in that situation magnetic field is getting changes here. So whenever magnetic flux linked with the coil changes, then EMF is induced here. This induced EMF is lost, so it means that this induced EMF is present as long as magnetic flux will get changes continuously. So in order to change the magnetic flux value, I am bringing that magnet closer. So it means that when the magnet is bringing closer means field value goes on increases. So magnetic field value increases here. So magnetic field value increases means what? So magnetic field value changes means flux value is also changes here. So when you take away from the coil, so B value decreases here, whether increase in magnetic field or decrease in magnetic field. In both the situation, flux value will get changes here. So that change in flux value can induce the EMF here. So next, in case of that Faraday experiment, so he moved further that, so depends upon the speed of that moment of that magnet into the coil, EMF value will get changes here. It means that the magnitude of induced EMF is, so it is directly proportional to rate of change of magnetic flux linked with the circuit. What's that Faraday's second law here? The magnitude of induced EMF is directly proportional to rate of change of magnetic flux linked with the circuit. E is equal to d phi by dt here. What's that value here? E is equal to d phi by dt here, where phi is nothing but a flux here. So E is equal to what? D by dt of NBA cos theta. So look at here, E is equal to what? E is equal to d by dt of NBA into cos theta here. So now in case of that Faraday experiment, he said that so there will be a EMF by changing the magnetic flux, but he didn't mention about the direction of induced EMF here. So in order to get the direction of induced EMF, so let me understand that Lenz law here. So that Lenz law will give the direction of induced EMF. So in order to understand that direction of induced EMF, so let me consider that Lenz law here. So what's that Lenz law here? So that Lenz law suggests that direction of that induced EMF here. So what is the direction of that induced EMF? I need to understand here. Okay, so next we will consider that Lenz law here. So that Lenz law will give the direction of induced EMF here. What's that Lenz law here? The polarity of induced EMF is such that it opposes the cause which produce here. So what's that Lenz law here? The polarity of, the polarity means sign, I can call that direction here. The polarity of induced EMF is such that it opposes the cause which produce. So what it means here? So it opposes the cause which produce means in which direction that cause is happening, so that EMF is induced opposite to the cause. So for example, look at here. So this is one copper coil. So this is the magnet here, north pole and south pole of the magnet. So magnet is moving here, so EMF is induced in the coil. So in this experiment, which is the cause here? Motion of the magnet is the cause. So if that motion of the magnet is the cause, means in which direction EMF should get induced here? Polarity of induced EMF is such that it opposes the cause which produce. In which direction cause is producing here? Cause is producing in this direction. Then in which direction EMF should get induced here? So opposite to the direction of the cause here. So EMF is produced opposite to the direction of the cause. It means that EMF can able to prevent the motion of the magnet here. So in this direction magnet is moving means EMF is induced opposite to the direction of the motion of the magnet here. So polarity of induced EMF is opposes the cause which produce. So it means that here motion of the magnet is the cause, means EMF is produced opposite to the direction of the cause. So look at here. Now in case of this circular coil, in which direction EMF is induced I need to understand. So for that purpose, for my convenience, so I can take that one coil here, okay, and this is north and south pole of the magnet. When north pole of the magnet is moving towards the coil, so in which direction EMF is induced I need to understand. So for that purpose, just you write the letter N here. If you write the letter N, so look at here, you may get that direction here. In which direction EMF is inducing here? So opposite to the cause which produce I said. So in which direction? So in a anti-clockwise direction. In anti-clockwise direction. So when that north pole of the magnet is moving towards the coil, so in which direction that EMF is induced here? In a anti-clockwise direction. Suppose if that south pole of the magnet is moving towards, or north pole of the magnet is moving away, both are same. So look at here. So this is the coil, sorry, one second, okay. So look at here, if it is a coil, south pole of the magnet, north pole of the magnet. So if that south pole of the magnet is moving towards the coil, in which direction that EMF will get produced I need to understand here. So in this situation, if south pole of the magnet is moving towards the coil, means just you will write the letter S here. So did you get the direction of that EMF here? It is in which direction? So it is in clockwise direction. Okay, so it is in a clockwise direction. So in order to understand that, so direction of induced EMF, I need to understand that Lenz law here. What's that Lenz law suggest here? The polarity of induced EMF is such that it opposes the cause which produce here. So it is a extended form of Faraday law. So E is equal to d phi by dt he suggests. Okay. So in which direction that EMF is induced here? Opposite to the cause. So I can rewrite that E is equal to minus of d phi by dt here. So what's that significance of this negative sign here? So negative sign indicates that EMF is always induced opposite to the cause here. So did you get my point here? Negative sign indicates that EMF is always induced opposite to the cause. If it has that number of turns, so minus of n into d phi by dt here. So this is the required equation for that induced EMF here. So now I want to calculate that induced EMF in a different cases here. So induced EMF, induced current and induced charges. So three properties I need to understand here in different cases. So induced EMF in case of that changing flux value, so changing magnetic field value, changing area value, changing angle value. So in all three aspects, what will be the formula for induced EMF I need to understand here? Induced EMF, induced current as well as induced charge I need to understand here. So let me consider that induced EMF first. So look at here. Let me begin with induced EMF. So look at here, in order to get that EMF, E is equal to minus of d phi by dt. E is equal to minus of d phi by dt. It means that whenever magnetic flux linked with the circuit changes, then EMF is induced here. Okay. So in order to change the flux value, so what shall I do here? Flux value is depends on what are the factors here. So flux value depends upon the magnetic field, it depends upon the area, and it depends upon that rotation or angle here. So look at here, In order to induce the EMF, I want to change that field value, magnetic field value. I want to change that area value and I want to change that angle or theta value here. So first, by changing the magnetic field value. So if I change that magnetic field value, so look at here, so phi of B is equal to what? So NBA cos theta. So by changing that B value, so EMF will be E is equal to what? Minus of d phi by dt here. E is equal to minus of d phi by dt. What is that phi value here? So if it is having number of terms, NBA cos theta. Okay, here I made that change in field value. So if it is change in field value means n into a into cos theta minus of n into a into cos theta b of 2 minus of b of 1 divided by t2 minus of t1 here. So look at here, minus of n into a cos of theta 1 b2 minus b1 divided by t2 minus of t1 here. By changing that magnetic field value, then here flux value changes. When the flux value will get changes means EMF will get induced here. E is equal to minus of n into a into cos theta b2 minus of b1 divided by t2 minus of t1 here, or I can rewrite here if that coil is perpendicular to the magnetic field here. So if the coil is perpendicular to the magnetic field means what is the angle between magnetic field line and normal line here? So coil is perpendicular to the magnetic field means angle between magnetic field and normal line is 0 degree here. So theta is equal to 0 degree. Then minus of n into a b2 minus of b1 divided by t2 minus of t1 here. So look at here. So I can write that b2 minus b1 divided by t2 minus of t1 here. b2 minus of b1 divided by t2 minus of t1. So I can write that instantaneous EMF in this case. Instantaneous EMF in this case. So E is equal to what? So minus of n into a d of b divided by dt. So this is the required equation for that instantaneous EMF in this case. In that second case, so I will change the area value by changing the area. By changing the area value. So similarly, I can rewrite this equation by changing the area value. So E is equal to minus of n into b into cos theta a2 minus of a1 divided by t2 minus of t1. Similarly, if theta is equal to 0 degree, minus of n into b a2 minus of a1 divided by t2 minus of t1 here. So or in case of that instantaneous EMF, I can rewrite that instantaneous EMF. So that is minus of n into b into d of a divided by dt here. What is that equation here? Minus of n into b d of a divided by dt here. So next third one, by changing the angle. So by changing the angle means, so E is equal to minus of n into b into a cos of theta 2 minus of cos of theta 1. Okay, sorry, or you can take that cos of theta 1 minus of cos of theta 2 t2 minus of t1 here. So let me consider that theta 1 is equal to theta 2 is equal to 90 degree. So in this situation, so E is equal to what? So E is equal to change in angle value minus of n into b into a, so d by dt of cos theta. So what's the value here? Minus of n into b into a d by dt of cos theta. So in case of that, so theta value, so theta, shall I take it as a omega into t here? So look at here, in terms of that angular velocity, theta I can take it as a omega into t here. So where theta is equal to omega into t, then this equation minus of n into b into a d by dt of cos of omega into t. So what is that differentiation of cos of omega into t? Minus of n into b into a omega into sine of omega into t. So differentiation of cos theta means minus. So look at here, E is equal to minus into minus plus here n b a omega into sine of omega into t. So here n b a omega I can take it as a E naught, where E naught represents that instantaneous EMF here, where E is equal to E naught sine of omega into t here. What's that E naught here? E naught represents that instantaneous EMF. What's that value of instantaneous EMF here? NBA omega. So hope you are understanding here. So instantaneous EMF in different cases by changing field value, by changing area value, and by changing angle here. So these are all the different cases here. By changing that angle means, so I got that equation that, so E is equal to NBA sine of omega into t, where NBA omega I can take it as a E naught. So that is nothing but an instantaneous EMF here, where E is equal to E naught sine of omega into t here, or E naught or maximum EMF, or so this is nothing but an instantaneous EMF. So look at here. So this I can call it as a instantaneous EMF or maximum EMF I can call. So instantaneous EMF or maximum EMF is NBA omega. So this is the principle of AC generator. So this will be the principle of the AC generator here. So now let me look at that. What is the value of that instantaneous current here? So already I got that expression for instantaneous EMF. Now look at that equation for instantaneous current here. Okay, next we'll consider that instantaneous current here. Instantaneous current. So in case of that instantaneous current, not that induced current, induced EMF, induced current here, let me consider that induced current here. So from that Ohm's law, I is equal to what? So I is equal to V by R, where V is nothing but a EMF, E by R here. So current is nothing but E is equal to, shall I write it as a minus of N into d phi by dt here. So E is equal to 1 by R into, so wherever E is there, so from that Faraday law, N into d phi by dt here, minus here. So I is equal to N by R into d phi by dt here. So look at here, so my negative sign. So I is equal to minus of N by R into d phi by dt, or phi of 1 minus of phi of 2 divided by T2 minus of T1. So phi of 2 minus phi of 1 divided by T2 minus of T1. I can rewrite this equation. So now let me consider that induced charge here. Induced charge. Look at here, induced charge. So I will use the same equation here. I is equal to V by R or E by R here. So current is nothing but what? Rate of flow of charge. So I shall write it as a dq by dt here. So E by R. So E by R, what you written here? E by R is nothing but what? So N by R into d phi by dt. Here dt term will getting cancelled out. dq is equal to N by R into d phi. Okay. So I want to integrate this equation. So integration of dq, minus of minus of n by r into d phi here. So integration of dq is nothing but a q minus of n by r. If number of turn is 1 means you can take it as a 1 by r. So initial minus of final. So phi of 1 minus of phi of 2. Integration of d of phi. Integration of d of x is nothing but x, or integration of d of phi is nothing but a phi here. Minus of 1 by r phi into initial I can take, so you can take this as the final, initial and final. Let me fill that limits here. Minus of 1 by r final minus of initial here. I shall rearrange here. Q is equal to minus is there, so shall I take that 1 by r into initial minus of final here. So from that induced charge Q is equal to, so phi of I minus of phi of f means change in flux here, change in flux divided by resistance, change in flux divided by resistance here. So let me write that induced EMF, already we got that equation here. Induced EMF value is equal to what? Minus of n into d phi by dt here. So look at here, induced EMF is depends on rate of change of flux here, and it is independent on the resistance. So look at here, induced EMF, there is no resistance term here. So induced EMF is independent on resistance here, and it depends upon that rate of change of magnetic flux. Whereas that induced current I can consider here. So induced current, it depends upon that rate of change of magnetic flux as well as resistance here. So look at here, induced EMF is independent on the resistance here, but whereas induced current is depends upon the resistance here. Now look at here, what about that induced charge here? Induced charge dq is equal to minus of n by r into d of phi, or you can consider here q is equal to change in flux divided by resistance. So induced charge is depends upon the resistance, but it is independent on the time here. So what it means here, induced charge is equal to change in flux divided by resistance. So induced charge depends only on the resistance, but that induced charge is independent on the time here. So induced charge is independent on the time means what it means here. So for example, so I will consider one magnet here. That magnet is moving quickly and slowly into the coil here. So first consider a magnet moving, first one slowly and second one quickly into the coil. So in these two cases, when the magnet is moving slow and when the magnet is moving quickly, in first cases, so in that first case, so induced EMF is less here, so induced current is also less here, because whereas induced current and induced EMF is depends upon the time here, both are less here. So what about the induced charge here? So induced charge is independent on the time here. So induced charge is independent on the time means, so induced charge is here and here, in both the cases same here. So it means that however fastly you can move the magnet, induced charge will be remain same. However you can move slowly or however you can move fastly, induced charge is independent on the time duration here. So induced charge is independent on the time here, whereas induced EMF is depends upon the rate of change of flux here, independent on the resistance here. Induced current is, so it is also depends upon the rate of change of EMF and it is depends upon the resistance here, but induced charge is independent on the time here. So however you